Welcome everybody, and thank you for joining us for this Engineering Science Postgraduate Research and Careers Evening. This is the first time we've done one in an online environment, so we'll see how it goes. So I'm Justin Fernandez, and along with Andreas, we are Department Postgraduate Advisors, and we're here to help you. And please do contact us to discuss any opportunities that arise out of this evening, or if you have any thoughts about next year or things that you're interested in doing, please do contact us. So this is the schedule for this evening, and you may have seen this being passed around. So we're going to have a quick introduction from our Head of Department, Piers Kelly, and then a number of presentations in different areas that we hope get you thinking about what an engineering scientist does. And then we're going to have a little bit of information on research and postgraduate environment. And after that, you're going to have an opportunity to meet some of our staff. So with that, I hope you do get a lot of information out of this evening, and I'll pass it over to Piers Kelly. Thanks, Piers.
Thank you, Justin. So, kia ora koutou, and welcome again, everyone, to this year's Engineering Science Research and Career Showcase. So this evening is about presenting to you opportunities to carry out research and study at the department. And for some of you doing your undergraduate degree now, or perhaps some of you have already graduated, you may well be thinking, I suppose, about enrolling in a postgraduate program. So if you are, I should say, first of all, you're in the right place. And I think doing postgraduate study here at Engineering Science, it's a great place to be if you enjoy learning, you enjoy problem solving, working with great teams, and you look forward to challenging and very interesting work. And of course, it's a great way to upskill in some area, specialize in some area, and for maybe some of you, even a change of area of interest or career path. And also, I'd keep in mind that what you do in a postgraduate degree gives you not just an advantage in the short term when you qualify, but also in the longer term when that education and research experience is something you've got right throughout your career. I'd also like to say that the Department of Engineering Science, it's one of the highest ranking departments for research in New Zealand. So the academics who work here and who you would be working with are internationally recognized for what they do. And any postgraduate degree you get here would be recognized in New Zealand and internationally as one of high quality. And you'd also be in good company as our postgraduate alumni. They now work in a wide range of industries in New Zealand and abroad, using their applied research skills, technical problem skills, problem solving skills, and analytical skills. And some of them also work in the top research institutions and universities around the world. So what I'll do now is I'll just say a word about the research we do. So I'm just going to share your screen. I'm just sharing this with you here. It's a diagram showing you the different areas and specializations in the department. So engineering science involves physical sciences, programming, mathematics, and data. And these are the three broad areas of expertise within engineering science. We've got operations research, where we use models to optimize and make better decisions. We've got data analytics and signal processing, where we explore data and signals and use these to inform. And we've also got computational engineering, where we develop models based on physical principles to simulate and predict the engineering and natural systems around us. And you'll see the broad range of applications involved. We've got transport, electricity markets, logistics, healthcare, machine learning, geothermal applications, and fluid dynamics, and as it says, much more, as it says there. And much of the research we do, and in fact, much of what engineering science is at the intersections of these. For example, the artificial intelligence, optimal design, and the and neural engineering, which use the skills and knowledge from a number of different areas. And that's what makes research at engineering science particularly exciting, is the collaboration across these various areas. So that's just a little taste of what you can explore in your postgraduate research and study. And next up now, you'll see some seminars on some of those researches. So I'll just end up there by saying I hope you enjoy the presentations and the rest of the forum, and I wish you all the best in choosing a satisfying and successful path forward from here. And if you do choose to do a postgraduate program with us, you'll be made very welcome at the department. Thank you.
All right, so I'm a bit of a younger face in the geothermal modelling team, and so I was just going to present to you some of the kind of consulting projects we do within the department from the university, working with some of our industry partners. So firstly, I was going to quickly explain who I am and how I got to where I am. I did undergraduate in the department a little while ago now, and I was kind of leaning more towards the continuum mechanics side of things. And after that, I kind of wanted to keep solving some cool problems. So I delved down into the very theoretical world with Richard Clark, and we were modelling the collective dynamics of microorganisms. So a fluid mechanics problem, looking at how these microorganisms interact and how they create cool patterns. And then after that, I was kind of looking for something a little bit more practical. So I talked to John O'Sullivan and his father Mike, and they offered me a job as a research fellow working on these consulting projects in geothermal. So I guess the point here is that if you choose to do postgraduate in something, it doesn't limit you to particularly a theoretical thing or exactly what you did for postgraduate. It just enables you to kind of have more of a basis in research and be able to move on and use that ability to learn now that you have to do whatever you want. So just quickly on the Geothermal Institute, I'm probably the least qualified to be talking about the Geothermal Institute as I just joined, but it was established back in 1978, and it's a research institute that is largely based in engineering science, but not entirely. And we have three main focuses: research and development, consultancy services, and education and training. And a lot of the research questions we answer come from the consulting work that we do. And as for education and training, we teach courses around the world about geothermal modelling. So at the moment, we're teaching a course in Iceland. We were meant to be over in Iceland, but COVID stopped that one. So we're teaching that one online at the moment. The geothermal modelling team is made up of approximately 38 people. This always fluctuates because we've got PhD students, master's students, and interns that come and go. And we're the largest dedicated geothermal modelling team in the world. And we've kind of got partnerships with a bunch of universities and research institutes around the world, such as GNS, Stanford, Reykjavik is a university in Iceland, and Delft is in the Netherlands. So yeah, we kind of a very collaborative sort of team, a big team in ourselves, but also collaborate out in the world. I showed this slide in the videos that you could have watched before coming along, so I'll just skip past it briefly, but we're looking for people to join the geothermal modelling team either as a graduate student, which would give you the freedom to do whatever you want, or as a research engineer, which is essentially an employee to work on these consulting projects. And we have a range of streams of different work that would appeal to different students. So whether you're into data and statistics, you can solve these cool inverse modeling or uncertainty quantification problems, and that would be working with Oliver McLaren and Rue Nicholson, or more modeling the real world systems, which is producing the results for the consulting projects, or developing the simulators that we do, which would lend itself more towards people that are interested in software development and high performance computing. This one here provides a quick snapshot of the projects that we've been involved in over the last, I think it's 2 years. So the ones in yellow are the consulting ones. So these are commercial projects we do that pay money to model real world geothermal systems. The green ones here are student projects. So we take on a lot of Masters of Energy students that model geothermal systems that are close to home. So we have a lot of Indonesian Masters of Energy students. So at the moment we've got 5 students modeling geothermal systems in Indonesia. And then we've got a lot of research projects around the world. In the East African Rift, there's a lot of hot fluid, and hot fluid requires different equations of state to model. So it's quite a few interesting research questions coming out of that as well. To give you a snapshot of how much consulting we actually do, our consulting projects bring in roughly $1 to $2 million per year. And again, here's a quick snapshot of what we've been up to in the last 2 years. So Wairaki and Ohaki are consulting projects we do for Contact Energy. Lihir is a gold mine in Papua New Guinea, and then we've got a range of other kind of interesting shorter term projects. And I'm just going to go through in a little bit more detail the work we do on 3 of these projects. So before we get into that, just the quickest summary of how we model these geothermal reservoirs. You take you model the whole geothermal system, essentially a bunch of water on top of a hot plate with rocks in it that have certain permeabilities. You model that up to a steady state, and then you match that to all the data that you have before you started doing anything to the system, like producing fluid. And then you match a production history to any transient data that you have. That might be mass flows coming out of wells, the enthalpies of the mass that is coming out of wells, or pressure responses in the reservoir that you can measure over time. And then you can, once you've got a model that's well calibrated to the data, you can use that to forecast forward. So this allows you to kind of analyze the sustainability of the resource and answer a whole bunch of questions that your client might have. So Wairaki is our longest term project that we've had. It's been a relationship with Contact for over 30 years. And this is one of the few projects in the world where we originally made some future scenarios predictions, and now it's been 20 years and we can go back and see how good those predictions necessarily were. So Wairaki is the big geothermal field as you drive into Taupo. And I guess this picture here sums it up pretty well, and this one will be quite familiar to engineering science students. It's become a bit of a hallmark for us. It's on various t-shirts, but what this is showing here is that in the Wairaki geothermal system, you've got these 2 big upflows, and over time we realized that these 2 upflows are connected, because we started producing heavily out of Wairaki, and then we saw a pressure response in Tauhara. So this connection here there's not necessarily good structural information to tell you that there is a connection, but through modeling we can kind of infer that there must be a connection, and then that's backed up by data and so forth. So we have this iterative process where numerical modeling kind of helps inform the decision making that goes on in Wairaki. The next big project I want to talk about is Lihir. This is for a company called Newcrest Mining. It's a gold mine in Papua New Guinea, and this is probably one of the most complex geothermal models in the world, because as you can imagine with a gold mine, the topography is changing over time. So as it gets mined out, the model has to adapt to catch up with that. And so we've got kind of interesting questions to answer here, because the geothermal system underneath the gold mine powers the gold mine, but also we've got another team that are interested in what kind of hot ground is coming is being mined. So we've got different outputs that we can do, and I guess this graphic here shows it quite nicely, that you've got this geothermal system that exists underneath the gold mine. Okay, the last project I quickly wanted to talk to you about is a very short-term project that we did recently. This was earlier in the year. We got an email from an iwi down in Rotorua, and they wanted to inquire about increasing their consented limit. They wanted to establish a new bathing facility down in Rotorua. And so they applied to increase this consent, and the Bay of Plenty Regional Council said, well, you need to be able to show that you won't have an impact on the surroundings. So we did a little bit of modeling work for them. And Rotorua is quite a unique geothermal system because you have hundreds of wells that are for personal use, not power production. And each one of these wells has kind of a consented limit on it. And the important thing in Rotorua is to maintain surface features and mitigate subsidence, because surface features are kind of important for tourism. So I guess here's a good graphic to show the Rotorua system. This circle here is the exclusion zone, so you can't take geothermal fluid within the zone. The blue dots are production bores, and then here is the location of the wells that the iwi are proposing to use for this facility. And close by, you can see that we have some surface features. So we did a little bit of modeling to show that if they increase their limit, they don't necessarily affect those surface features. So it should be okay to do. And they kind of came to us with a whole range of questions that they wanted answered, and we dusted off a Rotorua model that we had to answer some of these questions about subsidence, effects on vegetation, what the chemistry is going to do, and so forth. So it goes from these big long-term commercial projects right down to some very short-term, really interesting sort of projects. All right, that wraps up for me. I'll pass you on to someone else. But yeah, if you do have any sorts of questions about geothermal, come and have a chat to us after. We've got lots of opportunities for postgraduate studies, or as I say, as a research engineer, helping out with some of these commercial projects.
So, yes, thank you and welcome everybody. My name is Mark. Sorry, just trying to get it. So my name is Mark Batley. This presentation is focused on kind of computational modelling, computational mechanics type of modelling. There are other people involved in this work, Piers Kelly, John Cater, Richard Clark. This presentation is mainly on the work that I do and Piers does, and a little bit on what John does. So Richard's going to talk to you separately, I believe. But it also, and this I guess is one of the features of engineering science, is that often we work with a number of other departments and disciplines across engineering on a whole variety of projects. So between us, or between Piers and myself, we work with people in mechanical engineering and civil engineering and electrical engineering, people across other universities, both in New Zealand and overseas and so on. So it is one of the features, I guess, of engineering science. We cover quite a wide range of areas. So a few too many words on this slide, but you know, one definition of what I do and what Piers does that I quite like is that we're trying to model materials that we don't really understand into shapes that we can't precisely analyze to withstand forces that we cannot properly assess. And the key bit is that we don't want the public to realize how ignorant we really are. So that's where the research comes in. We need to understand how to analyze complex mechanics problems, how do we validate that they're correct, and how can we apply them. A few of the topics, I won't spend much on this because I'll talk more about them. There's work around materials, there's work around manufacturing, there's work around the structures and how they behave, and there's work around understanding what the loads on them are and what that means. One example of materials are foam materials, and these are the kind of structural foams that get used to build boats or aircraft or trains or other types of structures. That video you can see on the right there are just 3 different materials that are slightly different, that are different chemistries. And you know, some of them under an impact load bounce off, others of them fracture, others of them explode. And we're trying to understand the mechanics of why that happens and how we can model them. So that includes, you know, PhD students trying to model every single cell in these type of materials and understand what effect the shape of the cells and the variability has. How can we, in cases where we can't afford to model it at this level of detail of the cells, how can we homogenize it and get the right kind of behavior? From a manufacturing perspective, you know, composite materials in particular are used in a lot of high performance products, whether that's aircraft, cars, wind turbines and so on. But how can we efficiently manufacture them so that it's time effective, cost effective and reliable? So this is particularly an area that Pierce works in. What I do work crosses over into this. There's a large research group based out of across in Newmarket at the Centre for Advanced Composite Materials that works on the understanding how the processes work, how resin flows through the material, how things compact, how things cure, and so on. And whether that's building a rocket or an electric ferry, or understanding how a fabric compacts so that you can understand how the resin will flow through it, there's a whole lot of really interesting mechanics problems that have real life, important real life applications and value. Additive manufacturing, 3D printing is a really topical and current area. One of the challenges with that is kind of high performance composite materials are not really able to be 3D printed well. There are some technologies out there, but we're working on new ways to print long fibers, thermoset resins, and so on. Part of that too is understanding how we model that behavior everywhere up to the right here, between what's from a molecular level to a fiber and resin up to a product level. So the whole multi-scale type predictions and how we manage to model things well and know that we're modeling them well. And that's an area that both Pierce and myself work in. Looking at the structural behavior, I do a lot of work in the area of why do things break, which is great because you get to do experiments and models that actually break them, which is always fun. How does a little wrinkle or a void in the corner of a sailing yacht mast affect how things behave? How can you detect the defects in them? I've had a master's student working this year with Rocket Lab, understanding how do you qualify rocket structures for flight, literally to go to the moon. What happens when things hit water, whether that's boats hitting waves or waves hitting things. What happens when things crash, whether it's a car or a plane, and so on. And what happens with it, products that work with people, sporting equipment, prosthetics, orthotics, and so on. How can we tailor the design to work better? I talked about scale effects. And again, how do we get from a wrinkle, which is the corner of it, how do we get from something that's at sub-millimeter scale, and what effect does that have on something that might be 90 meters tall? So from an experimental and a modeling perspective, how can we understand the physics? How can we model it? How can we predict it accurately? How do things that you do for manufacturing processes? This is a recent PhD student working with BMW on the manufacturing processes for their composite electric vehicles. How does that affect fatigue life and so on? And then we get into the loads cases, the kind of multi-physics side of this. And in my case, I do a lot of work on what happens when things hit water. So whether that's boats hitting waters, boats crashing off foils, or waves hitting things. This bit of video of a boat coming down. This is an experimental facility at Newmarket. To the left of that is a fluid structure coupled finite element model looking at the stresses in a boat for a local company. Again, building out a PhD, many years of PhDs, going into master's projects applied to particular applications and so on. Then we move into optimization. So taking the kind of optimization techniques that you use in your degree, how do we apply them to structures to make them lighter, faster, stronger, or whatever? Then we get into the other side of waves, which is when waves hit things. And this is Tamaki Drive up on the right here in Karimarama, and a big storm down Hamoana, down in the east down near East Cape and so on. We're increasingly getting higher sea level, bigger storms, lots more damage. So how can we understand the physics of how these waves occur? What happens when they hit objects? Doesn't matter whether the object's flexible or rigid. How can we use that to develop better guidelines as to how to approach this? What are the good engineering solutions? How can we use biological solutions, be that plantings and so on, to improve things? And again, that's a collaboration with civil engineering. Then we're almost through here. Another example of multi-physics is inductive power transfer, and this is a topic that Pierce works on. So if you rather than having to plug your electric car in, be great if you could, in the first instance, just park in your garage, and just like your electric toothbrush, it uses inductive charging to charge it. Even better if you can stop at the traffic lights and it charges it. Better again if you can drive down the road and charges it. And this is a large area of research within the engineering faculty, one of the leaders in the world in this. One of the challenges here from an engineering perspective is how do you combine, how do you deal with the fact you've got electromagnetic behavior, you've got temperatures, you've got mechanical properties when a wheel rolls over it. And so both in terms of the underside of the car, of the vehicle, of the car, but also what goes on the road. And so how can you understand the physics? How can you model it well? How can you apply that to improve the world? And then you get out of the world. And this is an area that John Cater's working in. I've mentioned I also do some work in this area. The Auckland Space Institute has a whole lot of interesting projects everywhere from the rocket, the ship structures themselves, a whole lot of work around satellite, around imaging, around data analysis. What can you detect from space? How do you plan missions? Plan missions? How does propulsion work, and so on? So there's a whole range of activities there, and you can check out the Space Institute's website or talk to John or others about that. So what are some of the opportunities? I mean, ultimately, and I think Richard Clark will probably talk a bit more about this later. It does come down to money. You need some kind of support to do postgraduates. There are a range of funding sources. If you've got a good GPA, then over 8, you're guaranteed a University of Auckland scholarship. That gives you the flexibility to work with a supervisor, define your topic to something that you're really passionate about. The university, we apply, bring in external grants. So, reasonably often we've got funding that we're looking for a PhD for. There are also opportunities where we can work with companies to apply for scholarships that can support students. So my project I mentioned with Rocket Lab, that was supported through Rocket Lab. Another one working on hydroforce for yachts was supported through that company. So we can create some opportunities through that. In my particular case, I've got funding available around this kind of biocomposites, 3D printing, 4D behavior. CACM has 2 grants in with the government at the moment. One which will be looking at flammability and from a modelling perspective, looking at how we model building flammability, how it affects the structure, but also plastics recycling, which is another area. So we'll know in September about those. And then there are also opportunities for master's degrees on a whole range of topics. So really just, talk to us. Happy to talk about these ideas or anything else.
Okay, so my presentation is a little bit different from the last 2. I'm not going to talk about very many details, but just give you an overview of who works in operations research in engineering science and the sorts of things they do. There are other resources on opportunities. I think Mike Jr. is going to give a talk after me on analytics, and I think there is some downloadable stuff that you can find on Epoch, which is our research group. I'm not talking about Epoch in detail in this. So the people who work in OR, myself, Cameron Walker, Andrew Mason, Mike O'Sullivan Jr., it is, Andrea Wraith, Tony Downward, and Andreas Kemperlea. And so I'd like to sort of just draw a distinction here between operations research and analytics. They kind of mean the same sort of thing, but there are kind of 2 distinct sort of tracks or threads of work. And so if we look at analytics, I like to think of analytics as being a sort of data-driven techniques for solving problems, and OR is model-driven. And if you look at a sort of a hierarchy of models, then in analytics, you start at the bottom level with sort of descriptive models of just gathering data. Google Analytics is an example of this, where you get descriptions that say, how many Twitter followers do I have? And then you get slightly more sophisticated and say, well, if I post something on Twitter, how will that affect the number of followers I have? And that's a statistical type of approach to see whether you can predict what might happen using a model, or not so much a model, but a data-driven type of statistical model. And then in engineering science, we tend to work mainly in the prescriptive area, or at least in the OR analytics group, which is how do we determine what we should do to optimize some objectives. So we're really focusing on optimization and making decisions, which is what the prescriptive part of analytics is. So most of the analytics you hear about in public, the public arena, is predictive and descriptive, and that's where most of the successes have been. but we are sort of focusing at this high end in prescriptive area. So in that area, you know, you can do things in a data-driven way or in a model-driven way, and the sorts of work I'm going to talk about in this presentation is on the right-hand side of this picture, in the model-driven side, and others will talk about the data-driven side. So the research in OR in engineering science is sort of, can be drawn in sort of 4 different areas. One is application of models in practice. So these are generally in year 4 projects where you take a model in a particular setting and you try and apply it to make some recommendations. In a PhD, you really have to discover some new knowledge. So in a PhD, you really need to develop a new model form, or some new theory, or some new algorithms. And all of this is sort of colored with this, these ideas of complexity and uncertainty. So as OR has gone forward, historically, you know, the models have become standard, like a linear programming model, and no one really works particularly in linear programming now as a topic. They're just applied, but then there are new sorts of models emerging with higher degrees of complexity, uncertainty, when new circumstances arise, and those have to be understood and dealt with by the development of new models and algorithms. And that's where the research comes in. So if you think about, for example, a new model development, you might want to say, you know, what's the impact of an uncertain future milk supply on Fonterra's profit? Then in order to understand the impact of uncertainty, you have to look at a model which incorporated uncertainty and acted in an optimization setting to optimize subject to that uncertainty, and then see if you actually could reduce that uncertainty, how that would improve the profits. So you need a specific sort of model to understand how uncertainty affects things, not just trying different numbers to see how the plans would change. You need a model that actually accommodates the optimization under that uncertainty. New theory, a question could be, okay, so if we're training a model using historical data, an optimization model, and we want to apply that optimization model into the future, then we don't know whether historical data, it's just a sample from some distribution that we don't really know. So how do we try and make it perform well when applied to future observations? We don't want to overfit it to the data that we've provided with. And there's a whole lot of theory that's been developed by people in the department to understand how that process should be done. The algorithms that we work on in many settings are very complicated because they involve problems of very large scale. So in the hydrothermal scheduling work we do with the electricity industry, we've got 52 weeks, and problems, if we were to formulate them as a linear program, would have 10 to the 52 variables. So that would be impossible to solve using Arobi or Cplex unless you did some form of decomposition. So decomposition techniques are continue being developed in our group and by other people in the department. And finally, you know, complexity is something that is arising all the time in models. New circumstances and situations arise. So we're just emerging from a COVID-19 pandemic, and in New Zealand, and you know, the complexity of the decisions that have to be made in this setting, you know, are really, really very high. We haven't seen these circumstances before, and so you have to think about new models to try and think about this. In the electricity sector where I work, you know, the incentives and taxes that you might put on agents to try and get them to invest in batteries and solar panels or in renewable energy, you know, highly complex effects going on there that you have to think of new models to try and represent. So it's not just a case of taking standard techniques that you learn as undergrads and applying them. You have to come up with new models and new ideas to kind of incorporate in these complex situations. So just generally, where are these OR models used? And I've just did a very quick thought experiment and thought, where are the ones that I'm familiar with? Used in the energy sector, Transpower uses these models every day. The Electricity Authority have a lot of models to understand security of supply electricity generators use them to make investment decisions. Fonterra has a model called signal demand that they use for planning their production of dairy products, which is a model developed overseas but based on optimization. The Ministry of Health, of course, uses SCI models, and it's been for COVID. I mean, the models developed by Tapuna Matatini and Sean Hendy and his group have been had quite a lot of publicity recently, and there are other SCI models that they also use. The Climate Change Commission use models for understanding how to move to 100% renewable energy by 2050, and some of our group at EPOC are working with them using the judge system. And then Andrea Wraith works with Auckland Transport on traffic models for understanding how to do transport planning. So these models are these optimization decision models are always being improved and developed, and they're being used quite a lot in industry and in collaboration with us. So just to finish up, if you want to do a PhD or a graduate degree in operations research, then there are kind of two questions to ask yourself. What sort of techniques am I interested in working with, and what sort of domain am I interested in working in? So we all have various expertises and aptitudes in different techniques as supervisors, but the main description of the work we do, I think it can be delimited in terms of the domains we work in. And so I've kind of given a list here of, I hope I haven't stepped on anyone's toes, but I'm trying to summarize the domains that people have expertise in. So Cameron and Mike Jr. work a lot in healthcare. If you want to work in healthcare, you should go and talk to them. And they also do some work in finance and in statistics. Andrea works in transport, multi-objective optimization and infrastructure, and Tony Downward also works in that area. We have the EPOC group that works a lot in energy, CO2 policy. So that's Tony and me and Jeff Pritchard in statistics. Andrew Mason does quite a lot of work with Tangata Whenua. He has a really interesting analytics project in Taranaki that's funded by the National Science Challenges. He also works in emergency services, ambulance scheduling, rostering. And Andrew and I also have some connections with Fonterra. So these are kind of the domains in which everyone works. If you want to do a PhD and you have a certain domain you might find interesting, you should go and talk to the people on this slide. And that's me. Thank you.
I'm going to talk about the sort of work that Cameron and Walker and I have been doing in our research group, Aurora, but I would sort of echo what Andy said, is that this sort of work is done by people across the OR group. So it's sort of reflective of operations research and analytics in practice, and how we work with real world people to help decision making. You can find my research group's website there. And a lot of the stuff I'm going to be talking about is also on that site. So for those of you who don't know me, I came through Auckland University, went to Stanford in my PhD. I'm now involved in operations research throughout New Zealand as the OR Society president, but also as a theme lead in Precision Driven Health, which is a large public-private research partnership, and as part of Te Puna Matatini. So actually Cameron and I have been involved in stand-up meetings every other day with Sean Hendy and the rest of the group on the COVID-19 modelling. They'll talk about a little bit later on. We do all kinds of things, so health, finance, but also other things, as you'll see as I go through the talk. So one of those is computing, and particularly cloud computing. So we've been working on optimizing the orchestration of cloud computing, and that's really the allocation of resources and where things like the flow of data traffic throughout a network goes. We're currently working as part of it's probably a edge computing or fog computing, are the two buzzwords for it, a company which is looking to link computers in households in order to provide high performance computing, well, not really high performance, mass computing for computer rendering or machine learning or other things like simulation. We've previously worked with Hewlett-Packard, and a lot of the work we do currently is based on Citrix systems, although we're going to move shortly to VMware once we get down to the new building. Probably the main thing that Cameron and I do is as Andy said, is work on health. So we've been working with hospitals in Auckland, particularly Minimal Hospital, but also North Shore Hospital. And we're now working with a hospital in Ningbo in China. And it's looking at using our algorithms to help patients get through surgery. So we're basically planning surgeries to ensure that patients will get through in time. We're using prediction of surgical durations to make sure that surgical sessions are well used, but not too well used, so they don't overrun in their time. And actually, those algorithms are being used for planning in Ningbo, and they're in a pilot there at the moment. Tom Adams is our PhD student he's just completed, and his work has been predominantly looking at the surgical scheduling, and we're right now drafting up a research program with North Shore Hospital and Waitemata DHB to see if we can help them with their surgical scheduling and actually other decision making in health. We've also with Auckland City and North Shore Hospitals to help streamline treatment delivery. So part of that was for cancer treatment, part of it's around radiology, and part of it is just getting people around the hospital on time. And a lot of that work is optimization, but also simulation. And so here I've got a simulation from quite a wee while ago now. So this is North Shore Hospital, and you've got elevators, and all of these door-looking things are wards or treatment departments. And over here, this bunch of people are the orderlies in the orderly basin. So what the simulation shows is people who need transport will start popping up at the doors, and the orderlies will go running off and go and find the patient they need to pick up. So here's one here, and they'll pick up the patient and start moving them through the hospital to deliver them to their treatment, or pick them up from their treatment, deliver them back to the ward. And this helps the hospital to determine what good rosters for the orderlies look like, what good dispatch policies for the orderlies look like, and hopefully in the not too distant future, maybe automated dispatch policies for orderlies. So that's one way we can help streamline the treatment of patients. One of the things we're doing more recently, and actually somewhat surprisingly to us, but it makes sense when you think about it, is the idea of applying a lot of things you do in health to construction. And the reason it makes sense is that construction has critical resources that are used in lots of different places, and health also has critical resources that are used in lots of different places. So we've been working with Hawkins, which is one of the big construction companies, and our colleague Vicente Gonzalez, who does a lot of virtual reality and augmented reality work in the civil engineering department, to do simulation optimization for construction. And so I don't know if anyone's been to the big new mid-school building, but this is what the piling plan for that mid-school building looked like. And then this is a simulation of that piling. And so here we have all the machines used for piling. We have the piles around the edge here. So this is the top part of the diagram. And using this, the piling contractor could look at the order in which they're doing the pile. So here they're sort of spreading it out and doing every 10th pile. Or they could try to do all the piles at once, which is what they actually did in practice. And the reason this is useful is sometimes the geology of the ground is not that well known. And so as you start piling in different sequences, you'll get a much better idea of when you're going to finish the piling. And in the real world, the piling finished 5 weeks early, and the main contractor didn't realize that this was going to happen. And so they weren't able to then streamline their pipeline of contractors to come and do the next part. So this sort of idea of the simulation of construction sites, and actually the broader idea of digital twins, I think is now starting to become really useful with the amount of data we've got. And so we're working on a digital twins proposal for construction using Internet of Things and simulation and VR, AR, but that also I think is going to spill over into looking at digital twins of health systems, for example. One of the other places that we've been working, and this comes into the COVID-19 modeling that I'll talk to you about just near the end, is the idea of using data-informed policy design. And so we've been doing this a little bit, and it involves looking at big data sets, which is the integrated data infrastructure, which is the big data set held by Stats New Zealand, and looking to see how do people move through government, what decisions are made that influence their trajectories through government, and are there policies that can help people move, help people who don't have good outcomes to places that have good outcomes. And so part of that has actually been the COVID-19 response, has been that in a very short time frame, and with a big focus on health. but we're looking at working with lots of people within policy, infrastructure, all kinds of different parts of government as to how to model this and help embed analytics and operations research in that decision making. We also have been working on water, and this is at a strategic level. So we have been helping a company called ICS Consulting work with water utilities such as Thames Water, and in fact they're just piloting software which has our optimization engines within it with South West Water. We're hoping that we may be able to convince Watercare to maybe try and use this software also. And so inside that, there's a lot of the stuff that Andy was talking about, which is operations research, but lots of uncertainty and scenarios embedded within that to try and create robust plans that take into account climate change, but also uncertainty in demand, and particularly uncertainty in supply. We also work in logistics, so we did some optimization models, and those taking my 761 class may or may not appreciate this because it's a lot of vehicle routing, vehicle route planning. And so we were working with a company called Sutong Express, who move, I don't remember the exact numbers, it's something like 20,000 packages a month. And so we help them design what their distribution network looks like, what schedules they should have for their trucks, and where they should do pickups and drop-offs. And so this one relates a little bit to what Mark was saying about inductive power technology. And this is something that I'm working with John Boys and Grant Kovich on. And for those of you who did 363, this is basically 363 applied to inductive power technology. And so you have a whole bunch of design decisions. They go into a model of magnetics, and they give a design performance, and you wrap the whole thing inside a meta-heuristic, which in my case was a multi-objective genetic algorithm. And so you sort of have this idea of designing the coils so that you don't leak too much out the side. And so if you look at this picture, this is from my model. This is a magnetic model of it, and this is the resulting design. And so we suggested they do some of these designs with the coils and reflective cores, and they've actually started testing those. And this has been extended to different geometry. So here's a double D pattern, which is you have your two main coils here. Here's the coils in the car, and here's some reflection coils there. And so we now start modeling what the leakage of the magnetic looks like around the side, and try and optimize the amount of power given to these, or magnetism, I suppose, given to these coils that are in the car, and not leak too much out the side. And so this has all been, this I think nicely shows how optimization can integrate with design to help build stuff which a couple of years ago the IPT guys hadn't even thought of, and then once they looked at our models, it started getting really interested in different ways of designing these pads. This is the last one I'm going to show you, and then talk a little bit about the kind of tools you use. So this is something I've been working on over the last month, and this is actually the spread of COVID-19 in counties Manukau. So it might be a little hard to see, but in all three of these pictures, there's one exposed individual in Mangere Central, and then you can see I've got seeds here. So there's 8 of the different scenarios. Nothing happens, and 2 of them actually, and one of them, the spread goes outside to the rest of New Zealand, then comes back into counties Manukau, and one of them, the spread starts happening locally. So we're up to 16, it takes a little bit longer, so I'm just going to speed those ones up. So this one you can see goes through and nothing happens, so this person here becomes green, and so they don't affect anyone. And this one here, you can see there's an outbreak, and so this is the Manukau Harbour here, this is Mangere, this is Pukekohe, and this is Waiuku here, and so you can see there's been quite a big outbreak. And then also this one here, you can see the outbreak was just starting to happen, and also under that scenario there's more outbreak across the county's Manukau area. This is done using geometry models and some of the, not quite the SEI models, but similar to that Andy talked about. And so this is an example of, this is probably more the predictive analytics, but we're now going to use this predictive analytics to try and help counties Manukau decide where they should be testing for COVID-19 in the future, to make sure they catch outbreaks before they get too large. Here's all the kind of stuff we use. So we're pretty, we use whatever we need to get the job done. So Excel, Tableau, etc. I'm doing most of my coding in Python these days, but certainly we use a lot of R, and we're integrating with all kinds of databases at the back end and so on. So it's very practical work, but it's we find that in these practical projects you also find very interesting theoretical problems to look at, as Tom can no doubt tell you. And not only that, we feel like we're making a really nice contribution in terms of impact to New Zealand and improving healthcare, and generally just helping New Zealand make better decisions. Thanks very much.
So one of my roles is as Associate Dean Research for the faculty. What that means is that, and it's kind of about 2 days a week of my time, in theory anyway. So what that is I help to try and coordinate research within the faculty, try and grow and encourage research within the faculty, represent the faculty to the kind of university activities that again are trying to develop the university's research capability and activity. What I'll just do here, just in a few minutes, is just do a quick run through some of a little bit of background to the university as a whole. Now, most of you are students here already, so some of this you'll know. And then quickly touch on a few of the areas, though you've heard about most of those. So, assuming, hopefully you're aware the University of Auckland is top university, engineering faculty in New Zealand, and is well ranked across the world. Our civil engineering department in particular is highly ranked. You'll see the other departments, some of the other departments who are ranked here. Engineering science doesn't really have a ranking because nobody else does it the way we do it. So we're on our own, and that's great, but it's fine. We've got the two campuses, so both, and some of you will have been to Newmarket. If you haven't already, hopefully you'll have that opportunity. Particularly from a postgrad perspective, there are a whole lot of really cool facilities there. Everything from the really large structural testing and civil engineering, from fluids testing, from materials testing, from electrical type activities, and then of course we've got this lovely new building at Simon Street, which has got a whole lot of great labs all through that as well. So got some nice capabilities. Our students, of which many or most of you are. I guess the point here, which you're probably not aware of so much, is in the postgraduate space, we have similar numbers within engineering of both masters and PhD students. In both cases, there are traditionally more international students than locals. We're always keen to have local students. It's often trying to persuade. It's a question of encouraging you to come and do postgraduate as opposed to going and getting a job. We're very much keen to have good numbers of local students, but the balance is pretty similar between masters, both taught and research, and doctoral students. We've got there's some plots here of student diversity. So we've got across all of university, all of engineering, we've got a fairly significant number of students of some form of Asian origin, European origin, similar numbers of Māori and Pacific students, and that's an area that we are very keen to grow, particularly, well, both undergraduate but also within postgraduate, and so there are a number of opportunities around that. And then some other students, a reasonable number of students actually from kind of Middle East and Latin America, African, and so on. From a gender balance, we're somewhere around, in fact, the last number I saw was 27%. The faculty's been putting quite a lot of effort into trying to grow the number of women in engineering, and are keen to do that postgraduate as well. And then, of course, we've got a reasonable number of academic staff split across departments, which say our local students be aware of any other students across chemical materials, civil environmental, electrical and computer, engineering science, and mechanical. And as a number of us have spoken about, we work with all of those other departments actually in our research area. Now, there's a lot of research capabilities and areas. I'm not going to go through all of these, but aside from to say, you've heard about many of these already, and these are all areas which this department in particular, we bring that modelling expertise to and apply it across and work closely with a lot of other groups. There's a few more, everything from earthquakes and Wellington got shook again today. I was on a research call with people down at Victoria University and GNS when that happened, which was interesting. So we cover a lot of areas. The other point from a postgraduate perspective is one of the really cool things about postgraduates, particularly PhDs, in normal circumstances, and hope that things go back to normal soon, is the opportunities that you as a student have to travel, to collaborate with other institutions. So, often to go to other institutions for a period of time. That might be everywhere from a couple of weeks to a year, to months, or even I've had PhD students do it for a year, and learn how they operate, learn about the research, learn about the country, and then of course there are conferences and travel, and again hopefully the world will settle back down to a stage that we can be doing that again. So really, you've seen most of these. I'll just flick through these very quickly. There's the operations research around resource management. There's the the scheduling type thing, whether that's ambulances, aircraft, or whatever. The aerospace systems development, mentioned in terms of something that John Cater and myself and others are involved in with Space Institute. The composites area I've talked about. This is part of the COCM lab at Newmarket. The plastics recycling, IPT work. Again, this is another Newmarket lab picture. So cell signaling. This is some work out of chemical materials, but it's work that Richard Clark and myself were involved in terms of molecular modelling of molecules for drug delivery. So it goes through a whole range of areas. The waves hitting things, shaping coastlines, hitting objects, and so on with civil engineering. The data analytics we've heard a lot about, and that covers a really wide range of areas. And the geothermal work, which again you've heard about. So really, that's sorry, just a quick snapshot. I mean, from a research perspective, postgraduate study is a really, all of us who are talking to you ended up here because of the opportunities that came through postgraduates. There are lots of opportunities for there's both academic pathways and there's industry pathways. From my own experience, actually there are a lot of industry pathways. The majority of my postgraduate students have ended up going down industry pathways. New Zealand industry does recognise the value of postgraduate degrees. So it's not, it's opening up opportunities, not closing them off.
Like Mark, I have a role in the faculty as well as being a member of the department. I oversee the postgraduate research programs, so the PhDs and the MEs, and I'll just quickly talk about anything that we haven't covered around how those programs work. So picking up on what Mark was saying, there's myths around postgrad. Only a small percentage of people who do postgrad end up in academia. The vast majority end up in industry. There's also a myth that it's going to hurt your bank balance. There's some statistics to show that isn't the case. My personal advice is don't do postgrad because of the financial incentive. Do it because it will lead to a more interesting job, a research engineer type job. As Mark said, it opens doors more than it closes doors. So just to talk you through the postgraduate programs that we offer here in Auckland, we have the diplomas, the postgraduate diplomas. There are different flavours of these. And the certificates, I should say, as well. So a postgrad certificate is 1 semester, a diploma is 2 semesters. We also have the PG Cert in geothermal as well, which Sadiq runs from the department. The diplomas can be a good way of dipping your toe into postgrad if you don't want a long-term commitment. They can also be used as a pathway if you don't quite have the grades to get into the master's or the PhD. And I'll come back to what those grade requirements are in a slide or so's time. Then we have the master's qualifications. We have 2 flavours of, well, two basic flavors of masters. It's a bit of a confusing landscape. We have our taught masters program, and that's called the Master of Engineering Studies. We have the 1 year or the 1.5 year version of that. And then we have the research masters, which we call the Master of Engineering. So it's only different by one word. And this is 1 year and 1.5 year as well. The 1 year is by thesis only, so it's working with a supervisor on a year-long project. There's also the 1.5 year where the first semester will be spent doing some taught programs. As well as those two basic types of masters, the engineering studies and the Master of Engineering, we also have some named masters as well. So the ones that are probably going to be most applicable to engineering science graduates would be the Master of Energy, which Rosalind sees, and then we have the Master of Operations Research. And then we have the PhD, and in engineering science we also run a PhD in operations research as well. In Auckland, the PhD is between 3 and 4 years. The average time of completion is 3.5 years, which is shorter than in some other places. In the States, for example, a PhD is usually more like 5 years. So the PhD option is actually quite a quick option in Auckland. So just looking quickly at the admission requirements, to get into a PG cert or a PG dip, which isn't actually on this slide, we're looking at a GPA of 3. And for the Master of Engineering Studies, we're looking for, well, actually it's 2.5 for domestic students for PG dip and PG cert. For Master of Engineering Studies, we're asking for a 4. For the ME and the MOR, we need a 5, and then to get into the PhD, we need a 6. And for those research postgraduate options, the PhD and the ME, you'll also need to secure a supervisor and topic, and that's where Andreas and Justin play a crucial role, because they'll try and hook you up with someone who works in the area that you're interested in. Of course, you know, it's quite common to approach potential supervisors as well, but if you're not quite sure who's working in an area that could supervise a project that you're interested in, then Justin and Andreas are the people to go to. So in terms of important dates, the PhD can start any month. The ME has 3 start dates. So for 2021, those are the 1st of March, the 19th of July, and the 1st of December. So you'll need to get your application in a few weeks before those dates. So there's plenty of time for the ME. And similarly, the Master of Engineering Studies is semester-based, and so that will have application dates for semester 1 and semester 2 starts. Okay, and then the all-important money matters. Some of this has already been talked about. In terms of fees, the PhD is just a little bit over 7,000 per annum for domestic students. And the Masters is between 9,900 and 10,500. And then there's some service fees on top of that, student service fees on top of that. The good news is there's scholarships. So there's the Guaranteed University of Auckland Doctoral Scholarship. And you're eligible for one of these if your scholarship GPA is greater than 8. So for a PhD, the scholarship GPA is calculated on your final 2 years, so your part 3 and part 4. So if you achieve that GPA, then all your financial troubles are over, because the university will give you a stipend of this year 28,200, and they'll cover your fees as well, and that will be per year, so that will cover a 3-year period. And then most students are eligible for a 6-month stipend extension as well. It's not guaranteed, but in most cases, if you need those extra 6 months at the end to finish off your thesis, then you can apply for the doctorate extension. There's also a scholarship for the Masters, the Research Masters, the ME, and that's a stipend of just over 13,000, and it also covers your fees as well. Again, to be guaranteed that scholarship, you'll need a scholarship GPA greater than 8. Now, this is where it gets a little bit confusing, and I've never understood quite why this is the case, but for a master's scholarship, GPA is calculated over your entire BE. So the doctoral scholarship is based on your last 2 years. The master's scholarship is based on your entire BE. People have already mentioned that there's sometimes project-specific funding available, so it's always worth asking potential supervisors whether there's any funding attached to a project that you're interested in. And of course, some students do self-fund as well. There's also some smaller awards and scholarships available, and if you go onto the university website and click on the study menu and click down, there's a link to scholarships, and you can have a look on there. There's a database that will tell you if there's any specific awards for your area of research. So certain areas of research might have some funding from philanthropic sources, for example. So it's worth checking out that database as well. And then the final thing I want to mention, because it's unique to the University of Auckland PhD program, the university will give you in engineering $2,900 per year to cover research expenses. So that covers things like conferences, software purchases, publication costs. So that really does allow you to take advantage of some of those overseas opportunities that Mark talked about. Okay, so I think that's everything I had. I'll leave it there, but if you've got any questions, always feel free to drop me an email.